If you spend enough time in the chem lab, you're going to do a titration or two. And if you're taking that chemistry class, you're probably going to be asked questions about titrations. Titrations are very common, and in fact, I made a video a couple years ago on tips for the perfect titration. I'll put a link in this video where I demonstrate proper technique for doing a titration. So if you haven't seen that yet, maybe go check that out first and then head back here, because in this video, I'm not going to recreate that video. We are going to be reviewing some basics. We're going to look at the calculations you'll need to do in a typical titration, and then we'll look at some AP exam style questions about titrating. So you will need a calculator and a periodic table for today, so go ahead and grab that and let's get started. Let's start with our essential knowledge statement for this section, 4.6-A1. Titrations may be used to determine the amount of analyte in a solution. The titrant has a known concentration of a species that reacts specifically and quantitatively with the analyte. The equivalence point of the titration occurs when the analyte is totally consumed by the reacting species. The equivalence point is often indicated by a change in properties such as color that occurs when the equivalence point is reached. This observable event is called the endpoint of the titration. So a lot to unpack there. Some vocabulary we'll get to in just a sec. But what is a titration? Titration in general is the process of determining a quantity about an unknown by adding a known solution to it. You're saying, I don't know what this is, but I'm going to react it with this, and then we'll see how they relate. Usually acid-base neutralization, but it could be precipitation or redox. And things you can determine, things like molarity is pretty common, molar mass, pH, etc. All right. If you need help with the vocabulary, there was a lot of vocabulary in that one. Here it is. So the titrant is the liquid being added to the unknown. That's in your burette. The burette is the item of glassware made for dispensing accurate amounts of that titrate. The endpoint is the point at which the titration finishes, where the number of moles of the stuff you're adding completely reacts with the number of moles of the analyte, whether that's moles of electrons, moles of hydrogens, protons, or something. And then the analyte is the liquid being tested. So a typical setup would look something like this. You'd have a flask, probably, maybe a beaker, and you're going to add some of your analyte to it. The burette goes above that. You dispense your known solution, and then you get the color change you're observing. There's lots of different ones. And when that happens, you note your final reading from your initial. So you can subtract them and get the amount that you actually used. Now, as I said, I have a video where I demonstrate the whole process. That's not this video. You can go to the other one. But if you want to pause the video and just jot these tips down for better titrations and then go check that video out and follow along, that would be great. When you get your data, you're going to need to do a couple of steps with it. All right, for the full set of steps, it's 3 steps. Use the volume and molarity to find the moles of reactant that you added from your burette. Then you have to use the mole ratio. Some of my students, especially at the beginning, forget to do the mole ratio part. You have to do the mole ratio to get moles of the other thing that you're investigating. And then from those moles, we're going to convert to mass or volume. Notice that it's 3 steps. And that 3 steps should kind of get your spidey sense tingling that, wow, this sounds eerily similar to stoichiometry that I've done before. And yes, it should, because it is stoichiometry. So I got a couple of maps here that include volume and molarity as part of the steps to go from grams or volume to moles, then to moles, the new thing, and then to whatever it is you're trying to investigate about the other stuff. So it is 3 steps. It's just like what we've done before, but we're adding the solutions part. Let's look at some examples. I've already worked them out, but here's the prompt. It's pretty common to standardize your sodium hydroxide solution with some solid KHP. That's potassium hydrogen phthalate, not phosphorus. And it reacts in a 1-to-1 ratio, and it's a good way to find out the molarity of your NaOH because that's kind of uncertain when we make it. So we needed a primary standard to do that. A 1 gram sample of solid KHP was neutralized by a 31.2 milliliter sample of NaOH. What is the molarity of the NaOH? So I want to know something about the NaOH, but I know something about KHP. Let's do the 3 steps to get us there. Now, I already worked it out. I was doing it live, but then we had a power outage on the Wi-Fi, so my clip didn't record. But here it is, a 1 gram sample of solid KHP. Here it is, 1 gram KHP. It happens to have a molar mass of 204.2 because remember that's phthalate, not phosphorus. 1-to-1 ratio, make sure to include that. Even if it is a 1-to-1 ratio and it doesn't change your answer, put it there so that your grader knows that you know it should have been there. So that you know that they know that you know that they know that you know what you're doing here. So there you go. That's moles. And then I took the number of moles divided by the liters, and I got 0.16 moles per liter at AOH. Okay, your turn. Similar type question. And that type question is right here. Here's hydrochloric acid and NaOH, and they react in a 1-to-1 ratio. So take a moment, pause the video, and see if you can find what is the molarity of the HCl solution. All right. If you did your 3 steps, similar to the last time, you might have gotten 0.467 moles per liter for the HCl, which is correct. And congratulations if you got that. Then you're kind of mastering these 3 steps. Let's do one more just like this, similar, before we get into the AP style type questions. So here's KOH reacting with a diprotic acid. That's 2 hydrogens, so it's a 2-to-1 ratio. And so make sure we got to make sure to take advantage of that along the way. A 1 gram sample of a diprotic solid acid was titrated with KOH. It took 32.2 mils of 0.25 KOH to neutralize what is the molar mass of the acid. Now this one is slightly different at the end, and I just want to show it to you without doing a pause the video unless you really want to. It's similar to finding molarity in that 3rd step, but it's a molar mass. But we want to know what's the molar mass of my unknown. Liters of KOH times moles per liter, and then it's a 2-to-1 ratio, 1/2, 2 KOHs for that, and I get 0.00415 moles of H2A that are in my sample. Now molar mass is always given as grams per mole, and this kind of gets people mixed up sometimes. You actually have to take the mass you know, you weighed it out, divided by the moles you calculated are in there from the titration, and then you can get the molar mass that way at 241 grams per mole. And now we'll finish up with some AP-inspired questions about titrating. And by AP-inspired, I mean more visual and maybe imagining a real-life scenario in the laboratory. Let's start with this one because it relates to reading volumes off a burette. Here's a volumetric flask. Here's the calibration line. You might recall there's only one on a volumetric flask. And if a student is attempting to fill the volumetric flask accurately, sketch the appearance of the meniscus relative to the calibration line. Okay, they want us to know that the meniscus of the water is going to be curved and curved downward because of the adhesive forces to the side of the container here. So our correct sketch should be something like that. They calibrate these based on the bottom of the meniscus once it's filled to the correct volume. So keep that in mind because of our next question. The burette above, here's a burette, and 2 close-ups of the volume readings, is filled with 0.0318 molar cobalt-2 chloride solution for a titration. The initial and final volumes are shown. Calculate the number of moles of cobalt-2 chloride that was reacted in the titration. Notice this one, first of all, is not asking us to predict how much analyte is in there or the molar mass or the volume or anything like that. It's just kind of doing the first step of our 3 steps. We just have to find out how much moles of the stuff you're starting with are you adding. Okay, so now we're not doing all 3 steps, we're doing one step. Second of all, note the volumes here. Take a moment and think to yourself, what 2 volumes would you actually write down? Because this is important. All right, I'll show you the 2 volumes that I did. First, I measured this one, and I came up with 29.55. Did you add the hundredths in there? A good measurement gives every digit your instrument gives you, and then an estimate for that space between the lines, if there is any. So this gave me 29.5, and then I estimated a 5. You could estimate a 4 or 6. They'll be okay with that. As long as you put that digit in there because you actually know it to a reasonable amount of accuracy. So this goes to the tenths, your answers go to the hundredths. And one of the things that drives people crazy about burettes when they first start using them is that they're numbered from the top down. Yeah, so you got to read it upside down. And then we typically then do final minus initial, so we get a positive value. So a lot of people like get hung up on that. But we are going to do final minus initial, 29.55 minus 3.37. And when you're subtracting, you keep the decimal place of the least accurate measurement, which is the hundredths, so 26.18 milliliters used. So you have to do that first. Then we're just going to do volume times molarity, like we did in the other problems. 0.02618 times the molarity that is shown to us. And I get 8.33 times 10 to the minus fourth moles of cobalt ion. Okay, now take a look at this. Now we are here in Unit 4, and we haven't done Unit 8 yet. And so you might not have gotten to the place where you have plotted pH throughout a titration. And that's okay, because that's in Unit 8. But one thing I can tell you is that when we get to Unit 8 and start looking at graphs like these, there's going to be a sort of a not very steep part, a very steep part, and a not very steep part. The middle of that very steep part is your equivalence point. So just make a note of that if you haven't seen this yet, and we'll come back to it in Unit 8. So the equivalence point is here at 40 on this particular thing. So a 25 milliliter sample of H2SO4 was titrated with 0.15 molar NaOH. The graph of the pH is shown above. Calculate the molarity of the H2SO4 solution. Now, half the battle is figuring out what we're going to be doing here. And I'm told I have H2SO4, and I've also got the titrant, which was NaOH. I need to know H2SO4. So that means I have to start with the NaOH, and it's going to be another one of those 3-step problems that we did at the beginning of this episode. So a little bit more, we have the graph to work with. So let me show you my solution. I'm going to have you try one in just a second. And so I have the 40 mils, and I've been told it's 0.15 moles per liter, so 0.04 liters, 0.15 moles per liter. That gives me moles of NaOH. That's what I know. Note the 2-to-1 ratio. I had to know that because this is diprotic, it's going to take 2 OHs to neutralize each one. So 2 OHs, 1 H2SO4. And I got this many moles of H2SO4, and I was told that it was in 0.025 liters for a molarity of 0.12 moles per liter H2SO4. Okay, one more, and it's a good one. You'll see lots of similarities to the one we just did. We have another curve. A 15 milliliter sample of oxalic acid, also diprotic, hint, hint, is titrated with 10.1 molar NaOH. The graph is shown. Calculate the molarity of the oxalic acid solution. Take a moment, pause the video, test your skills, and meet me back here in a minute. Okay. When I did it, I got 0.067 moles per liter of oxalic acid. 0.02 liters, that's right off the graph. 0.1 moles per liter, again, 1/2, 2-to-1 ratio. Got me that many moles of oxalic acid in the volume that it's in, and I got 0.067. So if you got that, great, wonderful. Then you're all set up. You're ready to go to ace your titration questions on your exam. Well, I hope you found the calculations helpful. Like I said, if you wanted to see a demo of a titration, you can head down next one in the playlist or in the link below. In the meantime, happy studying and have a great day.